Hey class, this week we are going to be learning about pointers. Um, in addition to pointers, we're going to be learning about memory addresses, the stack versus the heap. Um, we're finally going to learn about destructors and when to deal with those with object-oriented programming, and then just some of the behaviors and syntax of pointers because it can get a little tricky. Although the concept isn't awful, a lot of students get lost um, when we start learning the syntax. So pay close attention, take notes, and hopefully it won't be too bad. Okay, so the first thing we need to understand is the concept of memory and memory addresses. So every time you compile a program, every time you initialize a variable, the program goes through and it finds the address of the memory that you're calling. So, taking the house example, every house has an address. This is what allows people like mailmen to know where to deliver the mail. They look up the address of your home, they go and deliver the mail. It's a really similar concept with C++, where each variable, each object, everything you declare in C++ has a value and it has an associated memory address. And the program behind the scenes has to go and point to those memory addresses every time you call a variable, every time you print a variable to the screen. It needs to go and reference that memory address. With pointers, we are manually going to be retrieving those addresses. That's the whole point of what a pointer is. It looks up the address, it points to it, and retrieves that address for you. So a little bit of an example here. On this screenshot on the left, I have an int x equals 7. So as soon as you declare x here, the program at compile time had to go and it had to retrieve and allocate memory and assign it an address so we can reference 7. So it went down to something called the heap, which we'll talk about in a minute, and it kind of made room for it and said, hey, this is where the value 7 is going to live, and here is an associated address with that. That's what happens behind the scenes every time you declare a variable. So I printed out x, and then right here, this little ampersand. Remember when we learned about references, we learned this concept. References are actually pointers. In more modern versions of C++, they knew that the syntax is a little confusing. They knew that people were making a lot of mistakes with it. So they decided to simplify it and give us references. But references are pointers. So when you look at x here, as soon as you put that ampersand, you're no longer retrieving the value of x, but you're retrieving the memory address of x. So if you look on the right screenshot, this is the output. Notice that I printed 7 here, and then I printed the address of x. And the addresses are going to look pretty similar to this hexadecimal code you see here. This is a memory address. So if you can forgive my lovely handwriting here, maybe I can explain this visually. So this is our code again, our similar version of it. Int x equals 7. So what's happening, if you were to visualize this, is the program went in and kind of made a space here. Made a space and held the value 7 and slapped a memory address on it. Okay, this x is just for our visualization, but really what's happening is we have the value of 7. This is the memory address associated with it. Then when we make a new variable, call it y, and set it equal to x, we are not setting y equal to this memory address. We are actually taking a copy of x and giving it its own memory address. So even though y equals x here, what's happening behind the scenes is the program is going in and making a new spot for y, giving it the value of 7 because it's a copy of X over here and giving it its own memory address. That's why when we pass things by reference in our code, that's more memory efficient because you're not taking copies here. You're actually just pointing to the original value. So hopefully that makes a little bit more sense. So every time you declare a variable, you are creating a new space in memory and it's getting its own address. So stack versus heap. Basically what happens is the stack is an organized form of memory. It has a data structure that's either a first in, first out, or a last in, last out. And basically, when you compile your program, what happens is behind the scenes it goes and it declares the scope of what you're dealing with. So remember when you, let's say you create a for loop and you declare the variable I. Remember I is our incrementer usually. Within the scope of that for loop, the program goes to the heap and says, hey, we need to make a spot for I, gives it its own memory address, pulls it into the stack here, into this organized form, deals with it appropriately, and then when you go outside of the scope of that for loop, when the for loop is over, it deallocates that memory. It says, okay, we're done with I, and it throws it back into the heap. When the heap is this unstructured memory. I think of this as my wife's sock drawer versus my sock drawer. The stack is organized. It has structure to it. There are matching pairs, and the heap is just a mess. So behind the scenes, every time you compile a program, it finds the scope of each thing you're working with, whether it be a function or a class, anything. It goes into the heap, allocates the memory needed, and then deallocates that when it's through. So hopefully that helps a little bit about what the stack versus the heap is, and that's really important with pointers when we start talking about allocating memory ourselves, which is what you do a lot with pointers. But first, let's talk a little bit more of what a pointer is exactly. So it stores the memory address of another variable instead of holding the value itself. It points to the memory location where the value is stored. So if you look down here, x equals 7. So remember, in our little example here, the program goes into the heap and it allocates and pulls it into the stack this value of 7 and assigns it a memory address. When you print out x, you are pulling the value that is held at this address. Right here, this next line, this is a pointer, and we know it's a pointer because of this little star here. When you do the variable data type and then you put a star right after it, you are saying that you want a pointer of type int in this case. And you can do all sorts of pointers. You can do string pointers, character pointers, doubles, arrays, anything that any data type that you can call normally, you can create a pointer of that type. And you just put that little asterisk right after it. Then you put the name. You can name this anything you want. And then this part is very important. You don't want to set p equal to x, because remember, x is 7. You need to set it equal to the address of x. And remember, the ampersand is what gets you that memory address. So if you don't put the ampersand here, you're actually going to get a syntax error. You have to put this. So notice that p is actually grabbing the address of 7. It's not getting 7 itself, it's getting the address of 7. So if you were to see out x, you would get 7. If you were to see out p, you would get the memory address, right? Another great thing about a pointer up here is a pointer manually allows the user to allocate memory from the heap. So In this case, we are not manually allocating memory. The program behind the scenes is allocating that memory for us, and we are just pointing to that memory that has been allocated for us. But in the next few slides, I will show that we can actually allocate memory ourselves and then create pointers that point to that memory in the heap, and then we would have to release that memory after. Okay, so how do we allocate and release memory? You normally only need to manually allocate memory kind of in two situations. There might be a third with polymorphism and when you're working with derived classes and all sorts of junk. But for simplicity, you really only need to allocate memory with two scenarios. It's when the amount of memory is not known at compile time or changes during runtime. And then the second scenario is when you want the life of the object to extend outside of its scope. So in English, this first point here is actually this example down here. A great example is with an array. Remember, with arrays, you have to declare the size of the array beforehand. Well, I kind of lied to you. You don't have to. But if you don't, you need to manually allocate what that size is at runtime. Because what happens is when you compile your program is allocating memory, right? It's saying we need this in this scope, and then we're going to have it for this long, and then we're going to release it. But when it's something like how big do you want the array, a dynamically sized array, and let's say we want the end user to type in like how many elements do you want to insert? 10. That can't be known at compile time because that's something that the user inputs at runtime. So if that's the case, and let's say they type in 10, how are we going to tell the program that we need 10 elements? Well, if you remember from our previous assignments, the way we went around this was we actually just made the array way bigger than it needs to be. So if they say 10 and you have it sized for 100, then you're good. But you can see that might be an efficiency problem, or it may cause bugs if the user puts something that's bigger than the bounds of the array. So to get around this, you can use a dynamically sized array, and you can do this by allocating the memory ourselves. So if you look at the screenshot here, int n, right, and then a cnn. So I'm asking the user to provide the size. Okay, this next line is the important part. Notice that I have a pointer of type int, I'm calling it array, equals, and look at this word new. This right here is what tells our program that we are going into the heap ourselves and we are grabbing and allocating memory ourselves. So it's new. And then what type of memory are we grabbing? Well, we're grabbing type int, and these square brackets mean that it is an array. And then inside here is where we put n. That's where we're saying how big of an array that we want. So pointer, and it's a pointer pointing to an int array of size n, right? And then this part is so important. If I can drill anything into your guys' head, it's this next part. When we manually allocate memory, we must manually deallocate it at the end of the program. And the way you do that is at the very end of your program, you would just put delete. Since this is an array, we put the square brackets after and then the name. If this wasn't an array, we would just put delete and then the name. If you forget to do this, you'll create something called a memory leak. You guys can Google some famous memory leaks with some big software throughout history. But basically, if you allocate memory from the heap and forget to deallocate that memory at the end, even when your program is over, this variable, this memory that's still in the stack just keeps growing and growing and growing. It's kind of funny. If you guys do this on accident, and surely you will at least once in your life, you may notice over time that your computer is getting a little sluggish. That's because the size of your variable from whatever program you wrote is just getting bigger and bigger and bigger until finally your computer crashes. If you do create a memory leak, you don't need to fret. If you just restart your computer, computers are really smart. When they start up, they'll check for memory leaks and they'll actually just deallocate everything for you. So it's not the end of the world, but it can cause big problems in your professional careers if you create memory leaks. So be very, very, very careful here, and get into the habit of writing delete. Okay, constructors and destructors. So this is actually the same concept as allocating, deallocating memory, but when we're talking about classes. So technically, every class you ever make will automatically create a constructor and a destructor for you. And we've talked a lot about constructors, right? This is setting up the default values for your object. If you don't write a constructor at all, kind of a default one is created for you behind the scenes. And that's the same with destructors. So normally, I told you guys not to worry about destructors because if you're not manually allocating memory, your program deals with it itself. But if we happen to create a class where we do need to allocate memory manually, then it is very important to write a destructor at the end. It's the same thing. You'd cause a memory leak if you forgot. So if you look at this up here, in your constructor, so every time you make a class object, notice that I'm making a variable and I'm calling it new, right? So I'm going into the heap and I'm creating new memory. Then it's, whatever, it's doing code, doing things. But what's important is, at the end, you need the destructor and you need to delete that memory. Now, we know this is a destructor because it is the same name as your constructor and it has this little tilde at the beginning. It's that little curly thing on the left of the one on your keyboard. It's called a tilde. So you put this and then you put your constructor name. You don't need to put any parameters in there. And then within that, you need to delete your data. You need to free the allocated memory. And that is essentially doing the same thing as creating new and deleting here. Okay, this part is a little brain bendy here. This is where a lot of people get hung up. But this is just the syntax of pointers. So, int x equals 7, right? We know what that's doing now behind the scenes. Now I'm creating a pointer, and that's what the asterisk is, and it is pointing to the address of x. That's what the ampersand is. Okay, we've established this before. So if I print x, I'm getting 7. If I print ampersand x, I'm getting the address of x. If I print p, which is my pointer, I'm getting the address of x. Now notice here, if I put asterisk p, I am actually getting the value of the address. So what it's doing is the pointer is pointing to the address, and then when I put the asterisk, I'm saying, hey, what value is at this address? Oh, it's 7. Okay? So printing out x and printing out asterisk p is actually going to give you the same results. Printing out ampersand x and printing out p is going to give you the same results. Okay? So now if we talk about dereferencing pointers, this part's interesting, and this is where references come in. Now we made a brand new variable. We called it y. What is the value of y? The value of y is the value of p. So now, contrary to what we did before with x and y, remember we did x equals 7, y equals x, and what that did is that created two spots in memory with their own addresses, both with a value of 7. This is not that. This is y is pointing to x, to that x value, to that address, and it's grabbing that value and assigning it to y. This right here is the same thing as a reference. Okay, so before references were introduced in C++, this is actually how you wrote a reference. So y is equal to the value of P, and P is the address of X. Okay? So now look at this. This is interesting. What if we set the value of P equal to 20? Right? Well, let's print Y. That's 7. Why is that 7? Because it is the value of P, and P is the address which holds 7. Okay, let's print P. It's an address. Okay. Now what's the value of P? The value of P is 20. Okay, well that makes sense because we put the value of P here equal to 20. Now what is the value of X? It is 20. Why is X 20? Well, we took the address of P and changed the value to 20. So that's like essentially overwriting the value of X from 7 to 20. Okay? When we're dealing with memory addresses and we change the values of the values held at those addresses, we are overwriting data. That's like working with references again. So we need to be very careful when we do this. All right, think about this for a minute. This gives you a value, a pointer gives you an address, and then the asterisk pointer is going to give you the value at that address. Okay. Last thing I want to talk about is specifically applicable to your homework assignment, and it's pointer arithmetic. Basically, you can grab pointers and you can increment them, or you can add to them or take away from them, and they will point to different spots in memory. So memory addresses are sequential. Okay, so if you grab this address and add 1 to it, you'd be looking at the next spot in the stack, the next memory address. So we have an array, has 3 values, and each value in this array has its own memory address. Okay. Now, if you took the address of array, you're actually just pointing, it's actually the memory address of the first element. So when I take a pointer here and I set it equal to array, notice that I didn't give it any positions, I just set array. I'm actually pointing to the memory address of the first element. So if I was to print pointer, I would get the memory address of this position. If I was to print asterisk pointer, I would get 1. Now I'm taking the pointer and I'm adding 1 to it, right? So remember, pointer is a memory address. So I'm adding 1, so I'm going to the next address. Now, if I was to create a second value and set it equal to the value of pointer, I would actually be getting 2 now because I've incremented the address. So this is important with your homework and also with that try it out assignment that you guys have done or hopefully will do. Pointer arithmetic is very important, and addresses are sequential, especially in arrays. Okay, that is all I have for this lecture. Please, once again, reach out if you have any questions. This stuff can get a little trippy, especially when we're talking about the syntax here. But if you guys can do this, you guys can be real C++ programmers, because this is the big hurdle when learning C++. So good luck, and please let me know if you have any questions.